Hello everyone, thank you for joining this webinar organized by the XFlow team of Dassault System SIMULIA. My name is Zaki Abiza, I'm from the XFlow business development team. In this webinar, my colleague Giuseppe Trapani, an XFlow application engineer, will present the new features of XFlow 2017X release, as well as the new integrated capabilities available with some Dassault system product that we have developed with this release. Before I hand over to my colleague Giuseppe, I want to inform you that you can send us your questions during the webinar through the questions dialog box you have at the right of your screen. So just feel free during the webinar to ask us your question. I will try to answer some of them during the webinar, and some of them will be answered at the end of the presentation by Giuseppe in the questions and answers session. Thank you again for joining us. I will let you now with my my colleague Giuseppe. So go ahead, Giuseppe.
Perfect. Thank you, Zaki. And hello, everyone. And once again, thank you for joining us today on this webinar on Introduction to XFlow 2017X. Okay. Again, I'm Giuseppe Trapani, and I'm a senior application engineer in the XFlow team. And today, I'll guide you through the presentation of our latest release, XFlow 2017X. And as Zaki introduced earlier, we're going to focus on some of the new capabilities introduced, but mainly on the integration with other Dassault system products. So we're going to see how we integrate with some of them and the different steps that we have in our integration plan. We also have a live demo, so we're going to try to show you some of the capabilities of the new release. You're going to see it's actually on one of these integration. So you can see live what does it look like, and then we have a question and answer session as well, so please feel free to pop up your question in the question and answer box or in the chat box of your GoToMeeting panel. Okay, perfect. So let's get started with the first part of the presentation, which is the new feature available in 2017X. And let's start with the multi-phase solvers. We already have a good variety of solver in XFlow, in particular the two that you are mentioning in the slides here. We have the particle-based tracking and the phase field solver, and those are really complementary multi-phase solutions which apply on different scales. So they cover basically the needs of a multi-phase simulation in XFlow. Now we're introducing a third one, which is the volume of fluid or VOF method, and it's actually somewhere in between the two ones already available in XFlow. Okay, so it uses some of the techniques of the particle-based tracking, so the interface is actually tracked in some way. It's not computed as an extra equation, but it does have some advantages over the same of the particle-based tracking. So, for example, the pressure field is computed on the entire domain instead of being applied as a boundary condition between the two phases. Okay, and that gives some advantages on type of simulation where we need less noisy pressure field. And the solver is again available as a labs mode in our XFlow 2017X. So the user will have to switch to labs mode to use it. But as you can see from the slides, it says it's adapted to large-scale multi-phase applications. So where the inertia forces are predominant over surface tension forces. Okay, a little bit like the particle-based tracking one. We have to say that in this solver, the tension effect, surface tension, are better captured than the particle-based tracking, but it's still not as good as a phase field, and just because the scale that we're dealing with are completely different. So it's really a first step development of this new solution for the user to use and well test on the specific cases. Okay, and now if we move from multi-phase to thermal simulation, we have a bunch of new development in the thermal solver, and we start with the top one, so number one, and it's the video that you can see on the right hand side of your slide. And there we have one of the new boundary conditions, and it's a temperature jump. We do have something similar in pressure, a pressure jump condition. So we ported that basically into the temperature field. So as you can see, some thin surface within this cylinder simulation, which enforces a temperature jump from the left to the right-hand side of the surface. Okay, it does not need to have a thickness, so it can be a thin surface, and that will set your condition. Okay, Some people use it on some specific simulation where they don't want to actually simulate the thickness and the change in temperature through the thickness of the geometry. So you can simplify your geometry in your simulation using the temperature jump condition. Okay, that's more into the, within the fluid domain, let's say. We do have a further development which allows us to specify convection and radiation condition on the outer skirt of our domain. So imagine that we have the same cylinder simulation in here, but we want to apply some sort of convection radiation condition on the boundaries of the external boundary of the domain, trying to simulate basically the heating or the cooling of the environment around the cylinder. Okay, so we developed and implemented a new conditions which is called convection radiation heat transfer, and you can apply that directly into the geometry, and simulate those heat transfer which are either by convection or radiation. So you can select, the user can select the contribution, and as you can see from the plot at the bottom right, we're trying to simulate in this case an increase in temperature inside the domain, and if you set that condition correctly and then you have the analytical solution, you can see the XFlow results are basically matching the analytical solution for the specific case. Of course, that's a simple simulation. It's actually a sort of a cube, but you can see that the law is correctly applied, and this boundary condition can be applied in a way to not actually solve the environment around the geometry you are interested in, but to mimic that effect as a convection radiation parallel system. Okay, switching to number 3, volume heat source. Again, you can see a typical application on the bottom left of your slide, and there you see, we are actually applying a volume heat into a porous volume. So that's a kind of a radiator simulation. So if you have, for example, a car where you have a radiator and it's a porous media, so you have a pressure drop of the flow going through, you can now in an XFlow 2017X add a volumetric heat source. So as you can see, we are plotting temperature in the video, and we're going to have an increase in temperature on the entire volume of our porous media, and of course that will actually extend on the fluid side. Okay, so in this case we have a velocity inlet from the left-hand side sweeping through the domain, and you can see how the temperature is then diffused downstream the porous media. Okay, so there is a good development for thermal analysis of, for example, in automotive industry. Okay, the third important introduction in XFlow 2017X is animated geometries, and that's something that's been in XFlow developed for some specific solver, but we kind of revamped the feature in the latest release. Specifically, we extended the validity or the applicability of that feature on all the solvers that we have in XFlow. So in this case, for example, you can see a video of a free surface simulation, and it specifically is a non-Newtonian fluid, so trying to mimic toothpaste simulation. And what the animated geometry allows you to do is to actually have a series or a sequence of geometries, so a set of meshes or surface tessellated geometries, as you can see here in .stl format. If you have those series that represent basically the deformation of your geometry, you can then use this time sequence of geometry to rebuild the deformation of the object with a specific discretization in time inside XFlow, and then use this deformation to drive the fluid flow. Okay, so in this case, what we have is different time steps of our geometry, our toothpaste and the tube, and we are interpolating in time the deformation, and we are squeezing out the liquid which is inside our tube. Okay, as you can see, some fluid structure interaction problem, but we are facing the one-way approach. So the fluid is actually affected by the structure deformation, but not the other way around, because the structure deformation is actually imposed on our simulation. And you can see how the tube deform the tube. Okay, on the left-hand side you have just the geometry, on the right-hand side you have the geometry and the fluid flow coming out. That's one of the application of such features. Moving to, probably a little bit less fancy one, but really important ones. For example, tires deformation. Okay, what we're trying to convey in this slide is the message that, well, we had few studies and few development on a conference in 2015 where they showed some advancement on simulating tire threads with simplified model. We now try to go even into more details, so we can say we can actually simulate the reality of how the tire deforms. So in that case, you can have a simulation in Abaqus, for example, for your tire deformation, export all this sequence of geometries, and then use that as a driver into the XFlow fluid simulation. Okay, you can imagine that we can use those type of features in simulating moving tires, so the entire geometry with moving tires deforming over time. You can include as many details as you want, like the actual road geometry scan inside the simulation. We have the contact patch, which is the actual one, so it's not an approximation of the contact patch. And you can use those simulations to do, well, FSI, of course, vibroacoustics, but as we can see in the next slides, even water management. So if you want to see what's or how does your tire perform in expelling the water using the threads of the specific geometry. What we see in this slide is actually a plot of the wetted surface on the left-hand side and velocity vectors on the right-hand side. Okay, so we can see how the patch evolves over time, and we have a tire that is pressed against the screen, so the tire is actually deforming on the y-axis, coming toward the screen. And we have a plot of the forces which the water actually applies on the tire on the bottom part of the video. And as you can see, as we squeeze the tire, of course we have fluid that goes through the threads, and well, there are high velocity regions, so the fluid is actually evacuated from the threads. And you can see the patch, the green patch, which develops, which is basically the place where water is gone because it's been expelled from the tire threads, and then the tire is actually pulled back. So then we have a release of these velocity vectors. Okay, so now simulations of, for example, tire or aquaplaning might actually be feasible using this technique. But we're going to see later on we can actually go further than that. We're going to see on some of the coupling with the DES technologies. So now changing in industry, going from automotive to marine, we do have, for example, lots of simulation with our partner WB Sail, and they're doing really impressive simulation with moving parts, moving objects, so pumping and rowing of the boats. But you can imagine to go even further and, well, set the sail as a deformable object. So you have some sort of history or some pre-calculated deformation of the sail, and then you can input that into your simulation. So you can actually calculate what's the thrust or the loads on the sail, not as a fixed object, but as an animated geometry, so as an object which actually deforms over time. Okay, of course that gives you more results, well, more realistic results on the loads that you're going to have, and some of the effects of interaction between sails and the hull, for example. Okay, so now I'm moving from more what I define as feature or new development to something which is a little bit more drastic in the XFlow development, which is what we define XFlow 1. Now XFlow 1 is basically an optimization of XFlow in terms of performance. So we're trying to squeeze the maximum from lattice Boltzmann method, and we have been working on that for the last year roughly. And what we're trying to do is actually optimizing the specific lattice Boltzmann implementation of XFlow. What does it mean? Well, in general, lattice Boltzmann is what we call a bandwidth limited method. It takes longer to actually access data, read and write, than computing something, okay? And the implementation usually is quite simple. On the computation side, it's more the access of the data, which is a bottleneck. That is usually true for lattice Boltzmann, specific for the cascaded lattice Boltzmann method, which is what XFlow uses as some sort. It's actually a little bit, well, less true, okay? It's a little bit more complicated to do some calculation, but 90% of the time is actually on memory handling. So the idea here is to try to optimize and maximize the memory bandwidth in order to reduce, of course, run times, computation times. We do have a specific development branch on that, and we have one of our best developer working on it, and he came up with a few tips and tricks to reduce the memory usage and to maximize the bandwidth. For example, reducing the load stores operation, being aware, or making a code is aware of the architecture of a NUMA configuration, so with multiprocessors, multi-caching, and try to exploit that. And of course, going to vectorization of the code, so trying to write a code which is actually a really low-level coding language, but exploits more the actual architecture, the hardware itself. Okay, so the process actually starts from the very beginning. So if you're familiar with XFlow, you already know that XFlow is a lattice postman code and uses what we call a lattice, so a discretization of our domain, mainly in points on space. And if you see this plot, you can realize that that's basically one of the cutting plane of XFlow, so where you can see one of the domain slice. That's what we call a point-wise structure refinement. So we can refine our simulation, going from black to blue to red, discretization lattice size. But that is not optimal, probably minimizes the number of elements, but in terms of performance, it's not the optimal case. So what we moved to is a different approach to the lattice generation, and that's what we call the block structure approach. So instead of creating just lattices, we create lattices but bunched in boxes, in blocks. Okay, here you can see 16 blocks, for example, and when we start refining our simulation, then we create block to refine. It's not just point-wise refinement. Okay, so we have the blue refinement and then the red refinement. As you can imagine, that increases slightly the number of elements. As you can see, a real case here on a car, on an auto vehicle, but it does give you lots of performance advantages. So for example, if you apply this new developed XFlow on a simple case like a lead-driven cavity compared to the standard XFlow, we can see here, for example, a factor of 10 speed up. Okay, that's a huge gain in performance. Of course, that's a simplified case. We have a uniform resolution, roughly 130 million elements, and as you can see, the scaling is almost perfect, 90% efficiency in scaling in MPI, but you have a 10x overall from 28 to 250 cores. Okay, so that's a really huge performance boost. Now, if you go to a little bit more realistic case, like the external aerodynamics I showed you earlier, of course now the lattice elements the structure becomes more complex. Still, we are around 100 million elements, and you can see we have a speed up anything between 4 and 5 compared to standard XFlow, which means a really big boost. And then we start dropping a little bit on MPI scaling. So the next step is actually to work on optimizing the MPI parallelization on the new architecture. Okay, so that's a really interesting development coming on this release, and it's already available for some specific simulations. Okay, it's not the entire XFlow scope. We just have some limitations. As you can see here, it has to be a 3D single phase isothermal simulation. There are some limitations on the function that you can use on the setup. So for the current version, only constant values can be used. We do not have the ability to do moving geometries, but then we can basically do any or almost any external aerodynamic simulation, okay, using a default wind tunnel in XFlow. Of course, we're seeing really huge performance boosts, so we want to port that to 2018, 2019. It's going to be to rewrite the entire XFlow feature, so from free surface to multi-phase to immersed boundary moving parts, and take advantage of this rewriting of the code and put a few inputs on, like some UDF, user-defined functions that can be actually compiled at execution time, so will allow the user to do some really interesting stuff with XFlow. And one of the, my favorite probably is the solver dispatches, so we still are working on a way to ease the life of a XFlow user, so that when it runs XFlow, automatically identifies what's the flow solver that it needs to use. And for example, if it has to choose between the legacy solver and XFlow 1, that can be done automatically by by the executable. It doesn't have to be a choice of the user. Okay, that's a big, short summary on the new capabilities that I wanted to show you. And now I actually move to the integration with the Dassault products, because I think we have really interesting development coming on this release. So I want to focus a little bit more on that and on the live demo. Okay, if you do have more questions, please don't forget to use the Q&A session or later on, or write that on the panel. Okay, let's start with the first Dassault product, or Simpack. So what we developed is two-way coupling with Simpack using the FMI standard, functional mockup interface, which is basically a sort of independent library or standard, and tries to support Cosimulation data exchange between different softwares. Okay, the configuration, as you can see on the right-hand side, is a sort of master and slave. And in this case, Simpack is the one that actually handles the master, so it's the master that calls XFlow in order to get the forces that it needs to do the computation. And all this information is exchanged using some libraries and FMI wrappers, okay? But really the user doesn't have to do anything else than set up the simulation and run it. What happened is, well, we're exchanging, like in this case, forces from XFlow to Simpack, and the other way around, the motion of the motorcycle from Simpack back to XFlow. And that is done determined time step, so the frequency can actually be chosen by the user. One limitation, well, we're actually exporting concentrated loads, so it's not a load distribution or a surface force distribution, but concentrated loads on specific points, which are probably the arrows that you see in the Simpack simulation. So those forces actually come from XFlow. And the idea behind this simulation is we have a motorcycle on a crosswind, so you can see that there is a wake that comes to the left-hand side of the rider. And of course the motorcycle will tend to deviate from the perfect straight line, and Simpack is trying to actually correct that, okay, and sending back the information to XFlow. So as you can see, that's a multi-body simulation with some sort of control of the riding line. Okay, let's jump to the second tool that we couple with XFlow, and is Dassault system or SIMULIA CST Solver. And what we basically do is take the electromagnetic simulation of CST, calculate the heat sources that produces, and then import that into XFlow. Now, compared to the previous integration, that's more a one-way coupling. Okay, so we read the results from CST into XFlow, but we do not exchange anything back to CST. Okay, so that's why the lines or the arrows are going one way. So we had two developments that basically enables this kind of integration, and one is the possible definition of a volumetric heat source, that now is possible to do that into XFlow. And the second one is a specific development, which is a sort of a new function that users can use to read into XFlow VTK, VTU mesh data. Okay, so a custom user know that they can use functions in XFlow to define input lows or velocity lows on motion lows, and now we have a specific function that can be used to read unstructured data, and that's the syntax that you can see on the top of your slides. So if we use this Unstructured Mesh function, we can read this file name and then use the input information as an input for XFlow simulation. Okay. The example we're seeing on this slide is actually a sort of heat source on a structured mesh that you can see on the left-hand side coming from CST, and then we are reading this mesh and this heat source into XFlow, and we are simulating that into a periodic box. Okay, you can see that at the beginning we are reading and interpolating the simulation from the unstructured mesh to our lattice, and then we are simulating that in XFlow. Okay, that's a simple example, of course, that we use for testing purposes, but you can imagine that we can go farther than that. As for this example, which is a stator, electric stator, and we have heat source or source term read in XFlow from CST simulation, and then we can do thermal simulation with CHT, conjugate heat transfer, in XFlow directly. Okay, of course here we were using as well the moving parts feature of XFlow. Good. Now let's move from simulation to geometry, and of course we couldn't do without trying to integrate Catia into XFlow. What we're doing in this case is we are showcasing how we implemented the DS special library in our latest release of XFlow, so that we can basically drag and drop CAD part and CAD products directly into our XFlow GUI. And as you can see, XFlow is able to read that file, and then you can choose the quality of your surface and edges, and then you create the geometry in XFlow. That is really, really useful, because now you don't actually have to export your geometry from Catia to a different format in order to import it in XFlow, but you can do that directly. So that's really reducing the CAD to CFD time to a minimum. Okay, let's go back to simulation after this small break on geometry handling, and let's go for, probably my favorite Cosimulation, that's integration with Abaqus. So now we are trying to do a two-way coupling between XFlow and a structure solver, and in this case we are indeed trying to do a full two-way coupling where we exchange not only forces on a local point but on a distribution on a surface. Okay. For that we are exploiting the Abaqus Cosimulation engine, and basically what happens is we're trying to exchange information on a surface. So we have forces coming from Abaqus and deformation, from XFlow, and deformation coming from Abaqus, and those are exchanged on this common surface. How does XFlow handle the deformed surface? Well, for XFlow it's just a moving body, so we can exploit the current capability of XFlow to handle those parts. We're gonna see a little bit later on how that is done. So let me jump to some of the videos and validation that we did on this specific development. And some people can remember we had a few coupling a few years ago, a coupling with an external structural solver, but that was limited for single phase simulation. Now with this new development, we basically have structural coupling with any solver that we have in XFlow. For example, on the top right side of the slides, you can see a coupling between the free surface solver of XFlow and Abaqus, and you can see how the information actually transfer between the two solvers. So we have a dump brake with a flexible bar, and those are interacting nicely on the right hand side. Okay, on the bottom side you can see the validation curve matching XFlow results with Abaqus PFM results. So that's the displacement of the tip of the bar. We also have, the same capability, of course, on single phase, and that's a typical benchmarking case, the Turek horn case. So where the vortex sheds from the cylinder are deforming the bar, and the bar itself is amplifying the vortex shedding. So it's a sort of a mutual interaction. You can see that the errors between codes, because that's as well computational results, there is no experiment on that, are actually really small. So the simulation is really, really, really precise. Now those of course are simple validation cases, but now if you recall we were talking about aquaplaning and deformable tires. Now we can go even one step further. So not only the tire is actually deforming because it's got a contact with the ground, but it's also interacting with the fluid, so the fluid will exchange forces with the tire, and we have this two-way coupling simulation with Abaqus XFlow free surface. And that is really key if you want to do analysis on, for example, aquaplaning, or again, water management of tires, or if you want to do simulation with actual threads or the actual geometry of the tire. Okay, so that really opens up lots of new simulation capabilities or possibility in XFlow Fluid Sturcture Interaction. Okay, that was all I had on integration with DS products. That was a quick overview, but that's to give you an idea of what's coming in the next release. And now I really want to focus on the live demo. So we'll take some time to show you what we're going to do, and we'll try to do a step-by-step setup. And what we're going to see, it's actually a reduced case of the validation that we saw earlier. So it's a flexible dam brake bar coupling. Okay, so we have the free surface on the left-hand side of XFlow and some really nonlinear high deformable geometries in Abaqus. Okay, and we're going to set up the case, and I'm going to show you how to run the case in Abaqus and in XFlow, and how the Cosimulation works. So the key things to remember in this demo is that we are using the new developed Cosimulation, CSE, Cosimulation engine, and it's a free surface simulation, of course. We're going to do a 3D simulation, although it looks like it's a 2D, it's just a 3D slice. Okay, and we're using Abaqus on the right-hand side, explicit dynamic, large deformation formulation, of course, and nonlinear elements. In theory, the coupling is developed for either explicit or implicit Abaqus, so standard, but we are going to focus on explicit simulation in this demo. Okay, so the user can actually explore different setup. It's the Cosimulation engine that takes care of the exchange between the two solver. Okay, so let me pause my presentation. Okay, and let me go and open up one of the XFlow window. So that's the new XFlow 2017X. Okay, this set a light color, so if you are seeing that in white instead of black, it's a different theme. Okay, so what we're going to do is we're going to set up an XFlow simulation of the dam brake, and at the same time we're going to set up the Abaqus counterpart. Okay, so let's start with Abaqus first, and I'm going to show you how to set up that quickly. So we start with defining our geometry first. Okay, we do just a part, so we create one. Okay, yeah, my dialog was probably on the wrong window. Yeah, let me check that. Okay. Create. Okay, and once we create the part in Abaqus, we're gonna set up the XFlow counterpart, and we're gonna set a internal simulation with the free surface solver. Okay, so let's do that again. Okay, 3D extrusion. Okay, and now we're gonna try to set our section, and if I recall correctly, we have those values for the section, which are 0.006 and 0.08. Okay, and if I do done, okay, 0.08, I think that should be my dimensions. Okay, yeah, I think it's a little bit too big on one side, so I'm gonna recreate that. 0.012. Okay, and let's do that quickly. It's minus 0.006 and 0.006 and 0.08. Okay, and if I do that, perfect. And my depth is 0.012. Okay, so now that looks much better. Perfect. Now we have our geometry. Let me quickly set the material, and well, we're going to define the density and of course some Young module. So elasticity, elastic one module, and we set a 0% ratio. Okay, it's nothing fancy. It's just a simple elastic model. Now let's set our section, and let's set this material, and we apply the section to our geometry. So now we're quickly setting explicit simulation in Abaqus, dynamic simulation. Okay, and as you can see, while I'm just creating the bar, I'm gonna now mesh it, and then we'll export that and set that as geometry in XFlow, structural geometry in XFlow. Okay, so that's my seeding, and I wanna mesh this part. So now I have a nice and mesh 3D bar, and we can move to the next step. So the Abaqus users will be all familiar with what I'm doing at the moment, which is basically creating the Abaqus model, so nothing fancy so far. I'm going to show later on two main settings that we need to keep mind on, which is interface and boundary conditions. Okay, so those are really important for the coupling of the two software. So now we have our assembly, and that's one of the steps which is important. So we have to define a surface, which is going to be our exchange of information. Okay, so I'm going to create one surface, and that is going to be a mesh surface, not a geometry one. Okay, because we're going to exchange information on the nodes of the actual mesh, and I'll select the whole geometry in this case, and of course we're going to have, well, the surface of all this 3D mesh are going to be the one exchanging information with XFlow. Okay, so now I have my surface 1, which is the surface where we exchange data. Perfect. Now let's quickly define a new step, and that is going to be, as we said, a dynamic explicit, and I'm going to call that a co-simulation step. Okay, now the only thing I'm going to define here is the time period, and it's 0.5 seconds. It's going to be exactly the same in XFlow, so we're going to have two simulations whose duration is going to be 0.5 seconds, and that is usually the case. Okay, you want your structural and fluid dynamic simulation to be exactly on the same simulation time. Good, so now we have our step, and that's step number 2. The user have to remember we need to create an interaction between the two software, so create an interaction in Abaqus, and we're going to call that a coupling interaction, and it's a standard explicit co-simulation coupling. Okay, so I do that, and of course I'm going to select the surface I created earlier, so my surface 1. Okay, and now I have my interaction defined, and as you can see, Abaqus is picking all the nodes on my mesh in 3D on the surface where I'm going to exchange information with XFlow. Okay, so now I'm done. Just a few boundary conditions. Okay, of course I'm going to set the base of this geometry to be constrained, so I'm going to set an encast in there, and let's do that quickly. So that's my boundary condition 1, and the second one I'm going to apply is actually a sort of a 2D displacement. So I'm going to select the remaining surfaces. I'm going to say, well, actually you can move on the X, Y plane. Okay, so not Z rotation, so not Z displacement and not X, Y rotation. Okay, perfect. So now we're ready. So we have our setup in in Abaqus. Let's create a job, and let's call that XFlow coupling. Okay, and let's keep the standard settings. I'm not going to do anything fancy. And once we are here, we are ready to run the Cosimulation. So we're going to write our input file for this Abaqus simulation. So if you right click on the job and write input, now we have our input file, and then we're going to use that to run our Cosimulation. So that's set, and probably the last step is to export this geometry. So let me do that quickly. You have in plugins, tools, STL export. I'm going to export the geometry as an STL file, so then I can read that into XFlow, and then I can use that to specify where the bar is going to be. Okay, so let's do that live, and let's call that bar. Perfect. So that's my export of the geometry completed, and now I'll do the setup in XFlow. Okay, so this is going to be a little bit quicker. So it's going to be a free surface simulation, and as we said, it's an internal one, and nothing strange in there. Perfect. Material, we're going to leave water as default. And now I'm going to first create my domain, which is going to be the exterior of my box that we seen earlier. Okay, 0.2, and that is going to be 0 and minus 0.006. So that's just the dimension of the exterior box, which is in there. Perfect. And now I'm going to read in the geometry I just exported, so the bar.stl. Okay, and as you can see, I read that in, and it's my starting geometry. Okay, perfect. So far so good. Now that's where the new thing come in. If you go back to environment in XFlow, now we have a structure analysis option, which is again available for labs or expert mode, and we can select Abaqus. And now we can select what's going to be the host name we're going to have the Cosimulation engine running, and that's the port that it's going to use. Okay, by default is 2024, but you can select any port that you can use for Cosimulation. Okay, so that's one of the settings we need to change in XFlow, is to select a specific structure analysis. And the next one is to set our bar geometry as actually a structural geometry. So instead of having a fixed behavior, there is going to be a structural behavior. Okay, so now XFlow will identify that the geometry is going to change over time, and the input is going to be given from Abaqus to XFlow. Okay, so if I visualize that, you can see that that's the exact mesh that we had in Abaqus. Okay, and that is going to change over time. Perfect. So geometry is done. Let me do a few other settings. And if I set a few boundary conditions, so on the sides, I'm actually going to set free slip boundary conditions. Okay. And that's because I don't want any friction on the sides of my domain. So that is going to be, instead of an automatic, a free slip condition. Perfect. Okay. And then I'm going to specify an initial height for my liquid. So as you can remember from the video, we had some height of water that then collapses and crashes into the bar. So I'm going to specify that in here. And I'm going to use a Boolean function. So that's another powerful thing of XFlow. You can specify function directly in the function viewer and use that in the simulation. So that's going to be a Boolean between X and Y. So I'm just filling up the left-hand side of my box. Perfect. So that is done. I have my boundary conditions, and now I'm setting my simulation time that, as we said, is going to be the same in Abaqus and XFlow, 0.5 seconds. I'm going to specify a custom time step in XFlow, and it's going to be a uniform resolution in this case, so my lattice is going to be all uniform and 1.2 millimeter. Perfect. We are ready. So now we have our simulation. So that's going to be 200. And I can save this one into the same folder where I saved my Abaqus simulation. And let's call it Abaqus demo. Okay. And now I have two set up ready. Now in order to actually execute the Cosimulation, we're going to have to do that in command line, but that's not a big deal. Okay, so if I go back to my same folder where I had my setup files, let me log in quickly. Okay, we're going to launch first XFlow and then Abaqus and then the Cosimulation engine. So we're going to have three windows open: XFlow, Abaqus, Cosimulation, and we're going to see how to do each step. So first of all, we're going to generate the XFlow domain, which is the lattice discretization. So that's the discretization of the volume we're going to analyze. Okay, that is completely automatic, so it takes a few seconds. And now we're going to execute the engine 3D FS, which is the free surface solver of XFlow. And as you can see, once you execute the solver, it's waiting for the Cosimulation engine on a specific host name, on a specific port number. And that's what we did specify in XFlow in there. Okay. Now we do exactly the same for Abaqus. So we run our Abaqus simulation. And as you can see, we're specifying again host name and port of the Cosimulation engine. And that's the XFlow coupling.imp file that we created, the input file. Okay, so once XFlow started, we start also Abaqus, and both will be waiting for our Cosimulation engine to start. So let's do that, and let's start the Cosimulation engine. And as you can see, it's an easy command. And again, we have the port number, which we specified earlier. So now Abaqus is explicitly starting up. It's doing some preliminary settings, checking. XFlow is already connected to the Cosimulation engine. So now it's waiting for Abaqus to start. And once we have our simulation starting, now we have both software, XFlow and Abaqus, communicating through the Cosimulation engine. Okay, so now the simulation is starting on the background. We're going to see that, well, as you can see here, the simulation is advancing on time, and we have a synchronization point at each specific time step that the Cosimulation engine controls. Okay, so that was the XFlow log. This one is the Abaqus log file, and all of that is, well, handled by the Cosimulation engine, which is easily set up using an XML file, and I'm going to show you quickly how that looks like. And that is delivered with the XFlow installation, so you can use the default settings. Okay, and that is basically standard setup for the Cosimulation engine, so the user doesn't have to modify that extensively, and then the simulation is running on the background. Okay, of course, what I'll do now is I'll show you the results, because we don't want to wait for the simulation to end. But as you can see, it's a really simple step, especially on the XFlow side. Okay, it's just setting the Abaqus settings on the environment, my structural geometry as, of course, a structure behavior, and that is basically it. Okay, so let's do some post-processing quickly, and I'll show you the final results of this simulation on XFlow first and then on Abaqus. So that's the exact same setup, but as you can see now we have a complete simulation. So if I move on time and I show some of the steps, well, you can see that the geometry starts to deform, of course, and if I do set a few cutting plane here and there, you can see how the fluid interacts with the geometry. Okay, let me set that exactly as the video so you can see where the video comes from. Okay, and if I, of course, select a different time step or step in time where I saved my data, you're going to see that, well, our geometry is actually being deformed by the forces acting from the fluid side. Okay. Now, just for comparison, let's quickly open up the Abaqus post-processing. So you can see exactly the same results that we saw in the video. So that's again the same setup we did earlier, and we're plotting von Mises stresses on this case. And of course, if I play that, you're going to see basically the deformation and the plots of the stresses on the Abaqus mesh. Okay, and of course that's a result of acting forces from XFlow passed by to Abaqus, and of course the deformation is passed to XFlow. Okay, nice and easy. And that concludes the demo on the coupling. So let me quickly jump back to the presentation, and I'll show you again the final results. So we've seen how to set this simulation up both in Abaqus and in XFlow. We've seen how to launch and execute the Cosimulation engine to handle the synchronization between the two software. And you can see you can do the live post-processing both in XFlow and Abaqus as the simulation evolves, so you can try to identify what's going on while the simulation is actually evolving in time. Okay, and with that one, probably I'll leave 5 to 10 minutes for questions if there is any. So please feel free to ask anything that you've seen so far on the presentation, or if you have any queries for the new release 2017X, we'll try to answer all the questions. If it's not possible, we'll then, well, either email you back or send you the reply through our contacts. And if you do have further questions that can come up later after watching this webinar, please contact us on our email address. You can contact Zaki on zaki.abiz@3ds.com or myself on my personal email address as well. Okay, so thank you for watching, and Zaki, if you do have any questions for me, please let me know.
Thank you very much, Giuseppe, for presenting us what is new in XFlow 2017X release, and thank you all for sending us your questions and attending this webinar. I have already answered privately some of your questions, but we will take here some 5 minutes now to answer more questions. So the first question for you, Giuseppe, is from someone who is maybe already using SIMULIA products. So it's about, so exactly, does XFlow 2017X use the license manager of Dassault system? I think he means the DCLS license manager.
Oh, okay. So yes, the answer is yes. We did implement the DSLS license scheme. So for this release, 2017X, we have the two options, RLM, which is our current scheme, and the DSLS one. Now that is totally true for Linux. Unfortunately, we do realize well, after the delivery of the package of XFlow installation, that in Windows there is a problem of, well, basically between the two license server. So the DSLS is not working for Windows, but it's perfectly fine for Linux. We already fixed that, so for the next patch release, we're gonna have DSLS for both OS, for both the Linux and Windows options. Okay.
Good. Okay. Thank you for this answer. Another question is more technical question on one of the first features you presented. Let me just find the question. Yeah. Can you explain the physics behind the temperature jump boundary condition? Can you explain more about the physics?
Yeah, okay, so the condition is basically trying to set a boundary jump or a temperature jump through a surface. So in this case, what we're trying to do is mimic if you have, for example, an heat source applied, or if you have some sort of cooling system or heat exchanger, instead of actually solving that using a fine lattice resolution or a fine discretization, you can mimic that with a surface. So it's a thin surface, it doesn't take long to compute, and then we're applying a delta temperature. In the specific case, we are setting 50% of the temperature lower on one side and 50% upper on the other side. So the delta is spread between the two sides. And as you can see well from the video, one side is cool and the other one is heat it up in a way. Okay, so that's the idea where you could use that instead of solving a really thin surface with lots of lattice elements. You could try to use that as a close approximation, let's say.
Okay, good.
Okay.
Yeah, another question. Just maybe one or two questions more, and we will finish this session. So one question is about the 3D Experience platform. If XFlow is or XFlow 2017X is available on this platform?
Okay, not yet on the 3DX directly, but we do work on a powered by option. So what happens, well, we have a sort of interface system between XFlow standalone and the 3DX platform, and you can basically access the data model of the 3D platform, 3DX platform, from XFlow through what we call the powered by option. So the data model will be read into XFlow, so you're going to have the geometry that comes from the 3DX platform. You're going to have your simulation, your system will of course record and have a tagging of the geometry that you're using, and then you can upload the results on the 3DX platform as well. So you're going to always have an associated set of results for your geometry. So this way you can keep track basically of what geometry has been simulated and what's the results, but still you do not have a graphical user interface of XFlow, let's say on the 3DX platform, or well, for this release. Of course, that's the long-term development, and we're working toward that, but in the meantime we offer this powered by solution to the user that can use the 3DX platform already.
Okay, so maybe the last question. Which are the software that could be connected to XFlow via FMI standard?
Okay, as I said earlier, it's a sort of standard, open standard, so many software implement the same format or the same standard. We've done that previously with MSc Adams, for example, another Multibody Solver. We've done tests with MATLAB or OpenModelica. So all these software that implement the same FMI standard, and there can be a master in the process, can be used with XFlow. And for the full list, probably the best way to do is to go to the website, OpenFMI. They try to have a sort of a list of software tested with the current version of FMI standard, so you can have an idea of what solver can actually be plugged into XFlow. That's the most updated list that you can get, is from the actual website of FMI developers.
Okay, thank you very much, Giuseppe, for answering the questions. I think we will stop here for this webinar. Please, if you have more questions, you can send them to me or to Giuseppe by email. We will try to answer them after the webinar. Okay, thank you. So thank you to everyone who has attended this webinar. I inform you that this webinar has been recorded, so you will receive an email notification tomorrow as soon as the recording is uploaded. This way you can review the webinar and share it anytime you need. So thank you again to everyone, and have a nice day. Thank you, Giuseppe, also.
Perfect. Thank you, Zaki. And thank you everyone for joining us.
Bye-bye.
Bye-bye.